The video will demonstrate how we can use the Xraster plugin to analyze multidimensional climate data to identify the harshest winters, assess the impact of global warming on heat waves in cities, and determine the amount of rainfall over watersheds during extreme precipitation events that cause flooding. In the Copernicus Climate Data Store, we find daily gridded meteorological data for Europe from 1950 to the present based on in-situ observations. This dataset covers all of Europe with a spatial resolution of 0.1 degrees, spanning from January 1950 to the present with a daily temporal resolution. When accessing the download options, we can specify variables and select different time ranges. Available options include daily mean, minimum and maximum temperature, relative humidity, daily precipitation, wind speed, and surface shortwave downwelling radiation. However, it is not possible to spatially restrict the data to a specific area of interest. The need to download data for the entire European region leads to large file sizes. For example, mean temperature data from 1950 to 2024 is 463 gigabytes. This presents a challenge in handling large datasets and subsequent processing. To mitigate this, we can easily download data as separate files for each variable, keeping the file size under 1 gigabytes per file. In the directory, we have separate files downloaded with the average temperature for Europe for the period 1950 to 2023. In total, we have 5 files. None of them exceeds 1 gigabyte in size. We proceed to the Xraster plugin. We go to Clip Join and create a text file with paths to individual netcdf files. We select the directory where the files are located. Click the New button and enter the name of the text file being created. Then click the Create button. The text file is created. Open the file. Each line contains the path to a file with data for a specific time period. Check if the files are sorted by time. With 5 lines, manual editing can be easily done if necessary. Now our goal is to create a dataset for a specific area of interest from files previously saved in a text file. To define the area of interest and possibly the range of analyzed depths, we open one of the downloaded data files. The file contains 5,476 rasters for each day in the period from 1950 to 1964, with dimensions of 465 rows, 705 columns. We proceed to the Subset tab. We will create a map for any given day to define the area of interest. We are creating a subset for the first day of August 1960. We proceed to the Figures tab and create the map. This is a map of the average temperature for a single day across all of Europe. We record the coordinates of the corners of the area of interest. And we return to the Subset tab, where we enter the window coordinates and click OK. We return to the Figures tab and display the map to check if the selected area meets our expectations. If everything is fine, we have defined the area of interest and proceed to the Clip Join tab. We use the Open button to load the created text file with the data files. We add a variable, enter the name of the new subset we will create, and click the Join button. After starting the subset creation process, the progress bar moves to 5%, then jumps to 100%. Creating the new subset may take a moment. Once the new subset has been created, we can go to Data to download it and check. In this way, we can prepare a subset of climate data for any area from the downloaded data covering all of Europe. The first project will involve creating a map of changes in the average winter temperatures in Poland between the years 1960 to 1980 and 2003 to 2023. In the project, we will use a dataset of daily average temperatures for the area of interest covering the period 1950 to 2023, along with a mask created for the area of Poland, where each administrative unit has a unique identifier. Areas outside the country's borders are assigned an identifier of 0. First, we will use the Xraster program to separately create maps for the average values in both periods. Then we will subtract the maps from each other using the QGIS program. First, we load the necessary data and the mask into Xraster. Next, in the Subset tab, we select the area where the mask identifier is 0, choose the winter months, and set the period to the years 1960 to 1980. Press the OK button. Go to the Statistics tab and create a map of average values for the first period. We observe that, for the majority of the area, the average temperature values are below 0. Save the map as a raster layer in GeoTIFF format. Now, go back to the Subset tab, change the time range to the second period, 2003 to 2023, and press the OK button. Go back to the Statistics tab and create the second map for the period 2003 to 2023. We observe that for the second period, the temperature is predominantly above 0. Save the second map as a raster layer. To create the temperature difference map, go to QGIS, open both of the raster layers you created. Go to the raster calculator and subtract the first raster from the second raster. We can now apply symbology to the created map. We can see that the largest increase in average temperature, reaching up to 2 degrees, occurred in the eastern part of the country. The smallest increase was observed in the south and locally in the north. Now, let's move on to the next project. The aim of this project is to identify the winters with the greatest ice cover on Puks Lagoon based on the average daily air temperature. A good proxy for determining the thickness and duration of ice cover is a metric called freezing degree days. It is a measure of how cold it has been and for how long it has been cold. The cumulative freezing degree days is usually calculated as the sum of the average daily temperatures below freezing over a specified time period. Here, I represents consecutive days during the period of January-March, and DT represents consecutive days. The summation is performed exclusively for temperatures below 0. We will use the same data as in the previous project, namely the average daily temperature for the region of Poland. The mask contains only a single pixel located on the edge of Puks Lagoon. This pixel has a value of 1, while all other values in the mask are 0. In this way, our data will effectively be summed from a single point. This means that for each day, only one value will be taken into account. We go to Xraster and input the data along with the mask. Now we go to the Subset tab and apply a filter so that only values below 0 remain, located in the pixel of the mask with a value of 1. We also limit our dataset to the months from January to March. We press the OK button to create the subset. Now we can go to the Figures tab and check the histogram of the created dataset. The histogram looks fine, with values only below 0 degrees Celsius. Our goal now is to sum the temperatures separately for each year and present the results on a graph. We go to the Group by Time tab, set the time period as year and statistics as sum. Then we press Run. Now we go to the Plot button to create the time series. Since the plot is difficult to interpret, we change its shape and set the draw style to steps. Now we can determine in which years the highest values of freezing degree days occurred. We can also adjust the starting point of the vertical axis to better illustrate when the harshest winters occurred. We can see that after 1990, harsh winters occurred only 3 times, and even then they were clearly milder than the harshest winters. With this observation, we conclude our analysis of the winter period, and will now take a look at how climatic conditions have changed during the summer months. We will now analyze extreme heat and heat waves during the summer period in Poland. In our project, extreme heat will be defined as the occurrence of temperatures equal to or exceeding 35 degrees Celsius. Meanwhile, heat waves are often defined in Europe as periods with temperatures exceeding 28 degrees Celsius, lasting for 3 days or more. We will adopt this definition here. We will use daily maximum temperature data along with the area mask for Poland previously applied. We will now move to QGIS. First, we will launch the Xraster plugin, then input the data and the mask. We proceed to the Subset tab to define a data subset. We will modify our data so that values of 1 are assigned to temperatures above 35 degrees Celsius, while all other values will be assigned 0. Additionally, we will limit our analysis to the area of Poland and the last 10 years, covering the period from 2014 to 2023. In the Calculate field, we first reset our variable by multiplying it by 0, and then add the expression ds2.t5 greater or equal to 35. ds2.tx refers to our variable, which represents the maximum temperature. If it has a value greater than or equal to 35, the expression in parentheses will evaluate to true, which is numerically equivalent to 1. If the condition is not met, it will numerically evaluate to 0. In this way, depending on whether the conditional expression is satisfied or not, our variable will be converted to values of 1 or 0. We will limit our subset to the period from 2014 to 2023. We will also limit our subset to the area of Poland by using the mask. Now we click the OK button to generate our data subset. We go to the Figures tab and display the histogram. We zoom in on the region around the value 1, and we can see that there are approximately 20,000 such values. Now, we will create a map showing the sum of days with temperatures greater than 35 degrees Celsius over the 10-year period for the area of Poland. We go to Statistics, and in the Time Statistics section, we set the statistics to Sum and click Plot. To better visualize the map, we will export it to a raster layer. Now we will go to QGIS, display the layer, apply symbolization, and set a certain level of transparency. We can see that the most days with temperatures above 35 degrees Celsius occurred in the southwestern part of Poland. Now, we will check in which year of the analyzed decade there were the most such days. We return to Xraster and go to the Group by Time tab. We will group our data by year and then generate a line chart showing the sum of cells with a value of 1 for each year. we see that the highest number of such values occurred in 2015. Let's create a map for that year. We select the year 2015, and by clicking Plot, we generate the map. This map shows a distinct hotspot in the southern part of Poland. Let's select a point in this region and then analyze the heat waves for this location in that year. We return to the Subset tab and limit our data subset to the selected point and the year 2015. We also restrict it to the months from May to September. Finally, we change the temperature threshold to 28 degrees Celsius. We go to the Figures tab and display the line chart. To better distinguish individual days, we add star symbols at the data points on the chart. Now we can easily identify successive periods with temperatures above 28 degrees Celsius and check if they qualify as heat waves. Here we observe 7 consecutive days from August 2nd to August 8th, meeting this condition. This analysis could be continued further. However, we will now focus on another extreme weather phenomenon, heavy rains causing floods. In this project, we will analyze the rainfall that led to flooding in the city of Kłodzko in southern Poland in July 1997. We will use daily rainfall data for Poland and a catchment mask representing the area from which water flows into the city of Kłodzko. In this mask, pixels within the catchment area are marked with a value of 2. Given that the size of a mask pixel is approximately 80 square kilometers, a rainfall of 1 millimeters over 1 day corresponds to 80,000 cubic meters of water falling on a single pixel. The main goal of the project is to determine the total volume of water that fell on the catchment area and caused the flood. We launch the Xraster plugin and input the rainfall data in the catchment mask. First, we will select the point within the Kłodzko catchment area with the highest rainfall to analyze its rainfall values for the entire data period. We navigate to the Subset tab, input the mask value of 2, and limit the data to the months of May through September. We press OK. The subset has been created. We navigate to the Statistics tab and generate a map showing the maximum rainfall values. We then identify the coordinates of the point with the highest rainfall. We return to the Subset tab and create a subset for the identified point. Next, we navigate to the Figures tab and create a plot showing changes in rainfall over time at this point. We observe that the maximum rainfall, nearly 175 millimeters, occurred in July 1997, coinciding with the flood. Therefore, we will limit our data to July of that year and convert the rainfall values into cubic meters. We return to the Dataset tab and create a subset of the data for July 1997 only. At the same time, we multiply the rainfall values by 80,000. Now we will group the data by summing the values for each day. We navigate to the Group by Time tab. We select the time period as day and the statistics as sum. Then we press the Run button and click Plot in the Time Series section of the panel. We have obtained a graph showing the total rainfall in the catchment area for each day. The flood on July 7th and 8th was caused by nearly 120 million cubic meters of water. The second wave of rainfall was half as large, and although there were concerns about it, it did not cause a second flooding event. We can export these data to a text file using the Export Time Series option. The exported file contains values for each day, which can now be further processed. In this presentation, we have showcased a range of possibilities for analyzing climate data. Thank you for your attention. Information about the program can be found in the About tab.